In this video, we're going to learn the difference of two perfect squares and what they are, okay? When we talk about the difference of two perfect squares, okay, we got to keep in mind it's going to follow this format. And when you factor this, okay, it's going to be just like this, okay? And why is that? Because if I FOIL this, okay, so you have a squared and b squared, and you're taking the difference of those two perfect squares. A perfect square is something that's times itself. That gives you that product, okay? So 49 would be a perfect square because 7 times 7 is 49. 25 is a perfect square because 5 times 5 is 25. A squared is a perfect square because a times a gives me a squared when I add the exponents. B squared is a perfect square because when I multiply b times b, I also get b squared when I add the exponents. All right, so if I FOIL this out, okay, a times a is in fact a squared. And then if I do a times minus b, that's going to be minus ab. And then if I do b times a, that's going to give me a plus ab. And then if I do b times minus b, that gives me minus b squared. Notice that the minus ab and the ab right here cancel each other out. So then I'm just left with a squared minus b squared. And that is the difference of two perfect squares. So if you want to factor this, this is going to equal this. You can factor it immediately by following this format. What times what is x squared? Well, it has to be x times x. What times what is 144? Okay, that has to be 12. And then, of course, one sign has to be positive, one has to be negative. It does not matter which one takes the positive as long as one's positive, one's negative. Those two factors, when you FOIL it out, will in fact give me x squared minus 144. And let's go ahead and do that. Okay, this is the answer. Okay, this is the answer that we have. And then if you want to check, to check, then you can go ahead and FOIL this out. Okay, you don't have to do this. I'm only doing this to show you that it will work every time. Okay, so x times x we know is going to be x squared. X times minus 12 is minus 12x. 12 times x is positive 12x. And then 12 times minus 12 is minus 144. What happens to the minus 12x plus 12x? They cancel. So now you're left with x squared minus 144. And that is your answer. Okay? So it does verify. Okay? Let's go ahead and do another one. Okay, so this is a perfect square. Okay, so we can just go ahead and fill in the parentheses. We don't need any special technique to do this. It's going to be done like this every time because it's a very unique pattern that will happen all the time as long as both of these terms are perfect squares and as long as it's the difference, not the sum. Okay, so what times what is 81? Well, it has to be 9. And then what times what is x squared? Well, it has to be x. So we have to attach the x's with those 9's. All right, since it's the difference of perfect squares, okay, what times what is 25? Well, it has to be a 5. What times what is y squared? Well, that has to be y. Again, one has to be positive, the other one has to be negative. And that is it. That is the answer. These are probably the easiest of the polynomials to factor because they have a very unique pattern. All right, but both of them have to be perfect squares. Okay. Same thing for this. What if I have this as an example? Okay? Again, this is a difference of two perfect squares. How do we know that? Well, look at the fraction 4 and 16. Both of those are perfect squares. What times what is 4? It's going to be a 2. The denominator 16, what times what is 16? That has to be a 4. Okay? And what times what is x squared? Again, it's going to be an x. So we're going to have 2/4 x and 2/4 x. Okay, look at the 9 in the other fraction, in the numerator. That's a perfect square, so it's going to be a 3. Look at the denominator of the second fraction, 25, right? What times what is 25? It has to be 5. So 3/5 and 3/5 go here. Okay, one has to be a positive, one has to be a negative, and now you have your answer. Okay? So let's do another one. Okay. In this particular problem, we look at 9k squared. That is a perfect square. We look at 49. That's also a perfect square. However, we will not be able to factor this because this is a prime binomial and this is not the difference of two perfect squares. So it cannot be factored using any other method either. Okay, so this is called a prime binomial. Had that plus sign been a negative, then we can proceed. Okay, so therefore we can't factor it. All right, so be careful with that. It only works with the difference, not the sum. Okay, so let's do another one. 64 take away y squared. All right, I look at 64. That is definitely a perfect square. So I'm going to go ahead and start filling in my parentheses. What times what is 64? It has to be 8. What times what is y squared? Well, it has to be a y. And then the signs have to be a plus and a minus. And there you have it. Okay? Let's do another one. X to the 4th minus 81. Okay, this is a good one because we look at x to the 4th. Is that a perfect square? It actually is. Okay, it actually is. Because remember, x squared times x squared, when you add the exponents, 2 plus 2 is 4. So when you're multiplying the same base or variable, you add the exponents. 2 and 2 is 4. What times what is 81? That's going to be a 9. And then, of course, 1's plus, 1's minus. Okay? So it's pretty straightforward, all right? You can be able to find the difference of perfect squares very easily, okay? Let's look at this example, and now we're going to talk about perfect square trinomials. Okay? And these also have a unique pattern that make them very easy to factor. So, this particular example, 27 y squared plus 54 y plus 27. Okay, so we look at this polynomial, it's a trinomial, and we want to see if there's any greatest common factors between 27, 54, and 27. And miraculously, 27 is in fact a GCF. So what we're going to do is we're going to take out 27 and we're going to factor it out. Okay, so we're going to factor that out. Okay, and then we're going to get something left behind. We're going to get the y squared stays behind. Plus, now 27 goes into 54 2 times. And then, of course, this has to be a 1 because 27 times 1 gives me the 27. So when you distribute the 27 back, you get the original polynomial back, and that's why there has to be a 1 there. Now we look at the polynomial right here, and that is a perfect square trinomial. Don't forget, this is the GCF that we needed to factor out. Okay, so the GCF needs to be factored out. Okay, and the polynomial that I underlined is in fact a perfect square trinomial. So when you try to do this, okay, let me just rewrite everything over here. We can factor this out by doing this. How do we know it's a perfect square trinomial? Well, we're going to look at the first term and the last term. Okay, so you basically look at the first and last terms and identify whether or not those are perfect squares, because if they are, then you have a perfect square trinomial. You don't need any elaborate method to factor. You can just fill in the parentheses, okay? And we can do that. Y squared is definitely a perfect square because y times y. And then, of course, 1 is a perfect square because we have 1 times 1. Now, since both signs are positive here, then both of these are positive. So that makes things really easy. Okay? And that is my final answer. All right? So let's do another one like that. And we look at this expression and we want to say, okay, is there a GCF that we can take out? So 48 and 27 are not perfect squares, and neither is x cubed nor y cubed. So when that happens, we want to try to factor out a GCF when possible. And in this case, we can factor out a GCF. The GCF between 48 and 27 would be 3. Now remember, if you're struggling with GCF, remember the method that I taught you. Remember? Okay, we'll do it off to the side. And we're just going to go ahead and start dividing. Okay, so there's a video that I made that teaches you how to find the GCF with that same method that I used to find the common denominator. Choose a number that starts dividing into these. The only number I can think of is going to be a 3. And a 3 goes into a 48. Okay, I believe it's 16 times. Okay, and then 3 into 27 is 9. Now, when you find the greatest common factor, you don't divide the columns down to 1 like you do for the common denominator. Here, we want to find a number that goes into both of them. Now, we're going to ask ourselves a question. Is there another number that goes into 16 and 9 evenly? Unfortunately not. So once you can't find another number that goes into both of these evenly, we will go ahead and stop. And therefore 3 is my GCF. So when you find a GCF, you keep dividing both numbers until you can't find another number that goes into both of them. If you have 3 numbers, it's going to be the same thing. You stop, okay? And so that's why I'm going to factor out a 3 here. Now, when you find the GCF between exponents, okay, so let's say you have, what, x cubed? We're going to do each variable separately. So the first term has a variable, has an x cubed. Here it's just an x. So, okay, so we're going to write that. When you take out the GCF, you take out the smallest one, the smallest exponent. Here's exponent of 1. So we're going to factor that out. Okay, so my GCF is going to be x. So that needs to be factored out. And look at the y. I have y in the first term, and in the second term, I have 20x y cubed. Which one do I factor out? I factor out the one with the least exponent, right? The smallest exponent. That's going to be y to the first power. They don't write y to the first because it's understood. So my GCF for that one is going to be just y. So I need to factor the y out. And now I have a polynomial that should have something left behind. Remember we said 3 goes into 48 16 times? That needs to go here. And if we have x cubed and take an x out, then there should be x squared remaining. And again, we pulled the y out of here, out of that first term, so that doesn't there. Put the subtraction sign, and then 3 times what is 27? Well, we said it was 9. And then we took out the x, and then we took out one of the y's, so that reduces to y squared. Okay? So we have to be able to find the GCF pretty fluently here in order to factor this. Now I want you to examine this. This looks like the difference of two perfect squares, doesn't it? 16 and 9. Okay, so basically we have 3xy, which we factored out. And now we can go ahead and fill in our parentheses. What times what is 16? 4. What times what is x squared? X. What times what is 9? It's going to be a 3. What times what is y squared? That's going to be a y. One has to be a plus, one has to be a minus. So this is my answer. Okay? So these are really good problems to get you used to factoring. Okay? All right. Okay, so that concludes the video. I hope that you found this to be very helpful. Thank you for watching.